Most people think AI just recognizes pictures, but that's not what really happens. When an AI sees an image, it doesn't see pixels, it decides what to pay attention to. And when it reads text, it doesn't read word by word. It looks at everything at once and figures out what matters most. This simple idea is what allows AI to connect images and language. Today, I'll show you how this works using a model called CLIP. CLIP stands for Contrastive Language, Image Pre-training. In simple terms, it means learning by comparing images and text. And by the end of this video, you'll understand the key idea behind modern AI systems that seem to understand the world. Are you ready? Let's go.
In CLIP, images and text are processed by two separate encoders, an image encoder and a text encoder. The internal structure of these encoders will be discussed in more detail later. In many CLIP implementations, both encoders are based on transformer encoder architectures and are trained using contrastive learning to align visual and linguistic information within a shared embedding space. Each image and text is converted into an embedding, and this process is repeated for every image and text in the database. After this process, each image embedding is compared with every text embedding. For this purpose, we use cosine similarity, which is an effective metric for comparing vectors.
But what cosine similarity exactly is? Once images and text are converted into vectors, the key question becomes, how do we compare them? The answer is similarity. When two vectors point in a similar direction, their similarity score becomes larger. In practice, embeddings are often normalized, meaning their lengths are scaled to 1. Because of this normalization, cosine similarity and the dot product behave almost the same. As a result, vectors that are closer together in space produce higher similarity scores, while unrelated vectors produce lower scores. This simple idea allows the model to measure how well an image matches a piece of text.
The resulting similarity scores are stored in a similarity matrix.
Now that we have developed a high-level understanding of the CLIP architecture and its core components, we can examine these components in greater detail. As discussed earlier, CLIP includes a text encoder that maps textual inputs into vector representations, commonly referred to as embeddings. It was also noted that CLIP leverages transformer-based architectures within its encoders. In the following section, we will therefore focus on the transformer architecture itself and analyze its internal structure and key mechanisms. Are you ready? Let's dive into it.
The text encoder in CLIP is based on the transformer architecture. While the original transformer consists of both an encoder and a decoder, CLIP uses only the encoder component, which is the part shown in the figure. To illustrate this process, consider an input sentence such as a blue dog. Before entering the transformer encoder, the input text is first tokenized, meaning that the sentence is split into its constituent tokens. Each token is then mapped to a numerical vector through an embedding layer. In addition, positional encoding is added to these embeddings in order to provide the model with information about the order of the tokens. Since the transformer architecture itself has no inherent notion of sequence order, after this step, each token, A, blue, and dog is represented as a vector in a continuous embedding space, as illustrated in the figure.
At this point, the words in the input sentence have been converted into tokens, and each token, after being combined with positional encoding, is represented as a vector. However, these vectors on their own do not capture any relationships between the words. Each token is still represented independently, without considering the context provided by the other tokens in the sentence. To model these relationships and allow each token to incorporate contextual information from the entire sequence, the transformer applies the self-attention mechanism, which we will examine next. Are you ready? Let's dive into it.
Each word is transformed into 3 new versions of itself: Q, query, K, key, V, value. To illustrate this process, consider the word dog with its embedding representation. Instead of using this vector directly, the transformer projects it into 3 separate spaces using 3 learned weight matrices. These matrices are learned during training and allow the same word to take on 3 different roles within the self-attention mechanism. Intuitively, the query represents what this word is looking for in the sentence. The key represents what this word offers to other words, and the value represents the actual information this word carries, which will be passed forward based on the attention it receives. Bear in mind that now, for each word, we have 3 different vector.
Up to this point, we have seen that each token is transformed into three vectors: a query, a key, and a value. However, these vectors on their own are not yet meaningful. By themselves, they do not tell us which words are important or how words in the sentence are related to one another. Their purpose becomes clear only when they are compared with each other. In particular, the query of one word is compared with the keys of all other words in the sentence. This comparison produces a set of scores that measure how relevant each word is to the current word. These scores, often referred to as attention scores, determine how much attention the model should pay to each word when constructing a context-aware representation. In the next step, these scores are normalized and used to weight the value vectors, allowing meaningful contextual information to emerge. Are you ready? Let's go.
From step 2, for each word we have 3 vectors. We want to answer one key question. Which word should each word pay attention to? For answering this question, each query vector is compared to the keys of all words with a simple dot product. The result is called attention score. These scores form the attention matrix and are passed through a softmax function, whose purpose is to normalize them into a probability distribution, ensuring that the attention weights are positive and sum to 1. The attention matrix shows how much one word attends to all other words. So in our example, by looking at the third row, we can see that the word dog attends most strongly to blue, since it has the highest value in that row. So self-attention is where the model decides which words should listen to which other words.
So far, we have seen that the attention matrix is constructed from the interaction between the query and key representations. However, this naturally raises an important question. What is the role of the value vectors? In the next step, we will examine how the attention mechanism uses all 3 components, query, key, and value, to compute the final attention output. Are you ready? Let's go.
These 3 components are ultimately combined using the attention operation. In this formulation, the denominator serves purely as a normalization term, ensuring that the attention weights are properly scaled. This step highlights a very important aspect of the attention mechanism. The final representation is obtained by computing a weighted sum of the value vectors, where the weights are determined by the attention weights. Look at this picture. The value vectors are combined using the attention weights of the word dog to generate a new representation for dog. Look at this connection. It is called a residual connection, and it ensures that we do not lose the previous meaning of the word dog, but instead refine it.
Up to this point, we have seen how the attention mechanism helps transform each word into a vector that not only represents its meaning, but also incorporates contextual information from other words in the sentence. But why is this mechanism called multi-head attention? In the image, the word dog is viewed through several different colored glasses. Each pair of glasses represents one attention head. Every head looks at the same word, but from a different perspective. One head focuses on how blue describes dog. Another focuses on grammar and sentence structure. Another looks at object relationships. Each head performs its own self-attention calculation with its own Q, K, and V matrices.
Finally, in the higher layers of the transformer encoder, each token is passed through a 2-layer feed-forward neural network. This network is applied independently to each token and consists of a linear transformation, a nonlinear activation function, and a second linear transformation. Its role is to further transform and refine the representation produced by the attention mechanism.
Up to this point, we have seen how the text encoder uses the self-attention mechanism to extract meaningful information from text. Now it is the image encoder's turn. This image encoder is known as a vision transformer, or VIT. A vision transformer works in essentially the same way as the text encoder, except that instead of words, it processes image patches, and each patch is converted into a vector representation. The same process then takes place for the image encoder. Image patches are projected into query, key, and value representations. Attention is computed through self-attention, and the resulting representations are further refined by a feed-forward neural network. At this point, you have seen all the key building blocks involved in contrastive learning: the encoders, the attention mechanism, and the shared embedding space. However, one important component is still missing: the objective function that guides the learning process. In contrastive learning, this objective is commonly referred to as the InfoNCE loss, also known in the context of CLIP as the CLIP loss. This loss function encourages matching image, text pairs to have high similarity while pushing non-matching pairs farther apart in the embedding space.
And the rule of the game is about as simple as it gets. If two things belong together, you pull their coordinates closer on the map. If they have nothing to do with each other, you push them far apart. That's it. That's the core idea. For the correct pairs, it tries to get their vectors to line up, giving them a super high similarity score. And for all those incorrect pairs, it does the exact opposite. It pushes their vectors away from each other, making sure they get a really low score. It's constantly adjusting to get better at this game.
Now that the model is defined, the next question is, how is it trained? In the following section, we'll address this.
So, how in the world do you teach an AI to do that? I mean, are you going to hire an army of people to sit there and write captions for millions and millions of photos? That sounds impossible. Turns out, OpenAI found a genius shortcut that was already out there, just hiding in plain sight across the entire internet.
And the secret ingredient? It was something called alt text. You know, it's that little description of an image on a website, mainly for accessibility. Well, here was the light bulb moment. The OpenAI team realized the internet was already filled with hundreds of millions of images that had these perfect human-written descriptions attached. The work was already done.
And when I say the work was done, I mean it was done on a massive scale. We're talking about 400 million image and text pairs. Just let that number sink in. They fed the AI this colossal buffet of data, and by consuming all of it, it started to learn the incredibly complex connections between what things look like and the words we use to describe them.
And that creates what the industry now calls a foundation model. And this is a really, really big deal. Think of it like building the foundation of a skyscraper. It's this massive, powerful, pre-trained base that has a general understanding of the world. And once you have that solid foundation, you can build all sorts of specialized apps on top of it, way faster and with much less effort. This foundation unlocks some truly mind-blowing abilities. The big one is something called zero-shot learning. This means the model can identify things it has never been specifically trained on. You could give it a description of, say, a zebra driving a tiny car, and even if it's never seen that before, it can find it because it understands the concepts. It creates this powerful bridge between what we see and what we say. So this all leaves us with a pretty fascinating thought to chew on. We've managed to teach a machine the language that connects our sense of sight with our words. So what's next? What about the language of sound, or touch, or even more abstract ideas like emotion or intent? What we're seeing here isn't just another step forward. It's like we've opened a door to a whole new era of what AI can be.
Thank you for watching and staying with me until the end. I hope this video helped you understand the core ideas behind modern AI systems, including attention, embeddings, contrastive learning, and the CLIP model. If you found this useful, please consider subscribing to the channel and feel free to share your thoughts or questions in the comments. Your feedback helps me create better and more useful videos. And stay tuned for the next videos.